All right, let's look at subspace. All right, so definition is pretty simple. All right, so if you have a subset W of vector space V, then W is called a subspace of V if W itself is a vector space. Right, so that's the definition. So it's a subset, but it is a vector space by itself. All right. So let's look at the simple result. It says this. It actually saves a lot of time. All right, so proposition 3.3. All right, so you have a non-empty subset W of a vector space. All right, so instead of checking all conditions of the vector space, we can only check just two. All right, W is a subspace of a vector space V with the same addition and the same scalar multiplication. And if and only if, W is closed under addition and scalar multiplication. All right. So one way, so if it's a subspace, then it's automatically closed under addition and scalar multiplication. So forward direction, forward implication is very clear. But the backward implication, so we only have to check two conditions, closed under addition and closed under scalar multiplication. Why is that? All right. So let's try to see. All right. So since we're using the same addition and the same scalar multiplication, from the vector space, so you can see that here we can check off a bunch of things like associativity because it's the same addition, so we can check that, and also commutativity, right? And let's see, associativity here for the scalar multiplication, and distributive properties, both of them. All right, so because since it's a same addition and a scalar multiplication, so we can check off right away. All right, then we're assuming that W is closed under addition and the scalar multiplication, so we can check off C1 and C2 because that's a given. All right, so remember we're trying to, right, this way is clear, right? But this way we're trying to do right now, all right? All right, so how do you know that there's going to be an identity, right? So identity is the zero, right? So additive identity. What you can do is take any vector V. Maybe I should do that. So take any vector V from W. Since it's non-empty, we should be able to find at least one. And then we can multiply by 0 from the field. So 0 times V is going to give you the identity, additive identity, right? So we know that such a thing exists, so we can check that off. All right. How about additive inverse, right? You can actually do a similar thing. We know that there's a -1 in the field, so take -1 and multiply by V, right? We know that this is going to be an additive inverse, right? So we could check off this, right? And here, the last one. What would be the identity? Well, actually, since we're using the same scalar multiplication, right? 1 is still in there, so 1 is identity is still there. Right, so we just needed to check a couple of things, and which is a closed under addition and closed under scalar multiplication. Then everything else is going to be pretty much given. So if you have a subset of a vector space, and then using the same addition and a scalar multiplication, W, the subset, is going to be a subspace. Right, that's it. I hope that this was clear.